Today's focus is going to be on interest problems, and we're going to begin with the point of comparison of simple interest. When you first learned about the idea of interest back in grammar school or middle school somewhere, this is probably what you were introduced to. Okay, the simple interest formula, A is equal to P plus PRT. Okay, A is the amount of money that you have at time T. That time T typically is in years, but it doesn't have to be. For interest, it's, I think for everything we do in this class it would be, but in theory for this particular formula it doesn't have to be. P is principal, which is the initial amount of money that you invest. R is your annual interest rate, and that's always put in as a decimal. Now, simple interest in the real world of finance really doesn't exist. Any interest that you're going to have is going to be some version of compound interest. Okay, now compound interest, our formula is A is equal to P, and then in parentheses 1 plus R over N to the NT. Okay, the A is the same A as it was there. That's the amount of money that you have at time T. P, same as it was there. It's your principal. It's the initial amount of money you invest. R is your annual interest rate as a decimal, same as it was here. T, same as it was here. The new variable is the number of times per year your money gets compounded. So, for example, if your money gets compounded once per month, that would be 12 times per year. That would be your end value. Okay, key difference here is the fact of we get linear growth versus exponential growth. So to illustrate that, we have $1,000 invested at 5%. So if it's in simple interest, T is equal to 0 means that's your time of investment. That's when the problem starts, was 1,000. You're going to get $50 per year interest, and that interest remains constant for as long as the money is invested in this account under those circumstances. Now, in contrast, if we were to take that $1,000, invest it at 5%, and have it compounded annually, we're still starting with the same 1,000, and at the end of 1 year, we still have $50. But what happens after that is the second year, we have interest on the principal plus interest on the interest. And then the third year, we have interest on the principal plus interest on the original interest plus interest on the new interest. So your money grows exponentially as opposed to linearly. You're getting more, the amount of interest you get goes up each year under a compounding scenario as opposed to a simple scenario. Okay, second idea we're going to look at. What happens as your end value changes? What happens as the number of times per year your money compounds? So annually would mean once per year. So that's your end value of 1. Semi-annually would be twice per year. Quarterly would be 4 times per year. Monthly, 12 times per year. Weekly, 52. Daily, 365. Now, in terms of realism, it kind of ends here. The rest of these are just for the purposes of building up a mathematical concept. Okay, what if it was hourly? That would mean 8,760 times per year your money compounds. What if it was minutely? What if it was secondly? And then what this morphs into is what if it's continuously? It just continuously compounds. All right, so what's happening here is the difference between annual and semi-annually at $10,000, 5% for 7 years means an additional roughly $59 in interest. From annually to semi-annually will get you roughly another $30 in interest. From semi-annually to quarterly, did I miss one here? Annually to semi-annually is about 58. Semi-annually to quarterly is about 30. Quarterly to monthly is about another 20. Monthly to weekly is about another 7, 8. Weekly to daily is only another $2. Daily to hourly is only another 32 cents. Hourly to minutely is only another 2 cents. So what happens here is we're reaching a limiting factor. It turns out that you reach the point where it doesn't matter how many more times per year it compounds, you're not going to make any more money. Okay, that's when it becomes the continuously. Now, one thing you may notice is it went from the 68 cents to the 71 cents and then back to the 68 cents. When you have denominators and exponents as large as this in your calculator, you're losing some precision. Okay, this is a round off error. That really shouldn't be 71 cents. That should be the same 68 cents as this and this. Just that your calculator can't handle that many decimal places to the accuracy we'd prefer. All right, now, one thing may look reasonably familiar to you. We started with an expression that looked very similar to this one of our very first days of Chapter 3. That was this guy right here. What we did was we took that expression and we put in increasingly larger values of n and realized that we reach a limiting value where this doesn't get any bigger. It reaches a limit of about 2.718, or e. Now, if you notice, the compound interest formula and the continuously compound interest formula, just on the rough surface, that 1 over 1 to the n thing gets replaced with r. Now, mathematically, there's a little bit more going on than just that, but roughly speaking, that should be the observation. So, this is the overall set of formulas we're going to be working with. Now, we don't really do anything in this class with simple interest, but the formula does exist. If it's simple interest, this is what you use. If it's compounding anything other than continuously, then you use this. If it's compounding continuously, then you use this. So in general, there are 3 formulas to choose from. For what we do in this class, it's going to be one of these 2 guys here. So again, compounding continuously, and compounding continuously only for interest is when we use this. This is compounding anything but continuously. Okay, for the example sheet here, we're not going to do all of these. We're going to do a sampling so you get an overall flavor of what's going on and the expectations in solving these guys. All right, so our instructions up top are to complete the following table for a savings account in which interest is compounded continuously. Okay, as soon as you see compounding continuously, it means you're working off the PERT formula. A is equal to PE to the RT. Okay, for part 1, they're telling us our initial investment is $3,000. Our annual interest rate is 7.5%. They want to know how long does it take our money to double, which is a very common financial statistic people like to know, doubling time of their money, and how much money we can have at the end of 10 years. So, let's take a look at the formula. A is equal to PE to the RT. The initial investment is the principal. E is the irrational number, excuse me, about 2.718. The interest rate is a decimal, 0.075. Okay, time, and then these 2 guys are interconnected. This is the amount of time, the amount of money corresponding with that time, the amount of time it takes to make that money, depending on how they word the question. So the first thing they're asking us to find is how long does it take for our money to double? Well, that means if our money is doubling, we want to know how long it takes 3,000 to be 6,000. And then solving for that t is what we're looking for. Well, divide both sides by 3,000. Natural log of both sides. Divide by 0.075. So, natural log of 2 divided by 0.075, and we're looking at about 9.2 years. As always, with anything we do in this class, make sure you follow whatever the round-off instructions are. There's nothing specific here. I'm just going to go 1/10 of a year. All right, the other thing they're asking us for, how much money do we have at the end of 10 years? Let me space out my work very well here. So that's asking us for an amount given a time. So this one actually mathematically is easier than the first thing we did. So 3,000 e to the 0.075 times 10. And unless you're told otherwise, if it's money, round to the nearest cent or 2 decimal places. So this is 6351, and then 2 decimal places, 00. Okay, we're going to do the second one here. Our initial investment is $900, and it's telling us it takes 20 years for our money to double. The initial amount, the principal, is the $900. It doubles when it becomes $1,800, and we know that takes 20 years. So if they give you the initial investment with the doubling time, the only thing that we can solve for working with this formula is our interest rate. We divide both sides by 900, gives you 2 on the left. Natural log of both sides. Divide by 20. All right, now for the purposes of filling in a box here, we have to put something like, we're looking at about 3.5%. But we need to use this number in order to get that value. So what we're going to do is we are going to avoid intermediate rounding errors by storing that value. What we're going to do is hit the store button, which is the SVO above the on, and I'm going to put alpha R as the variable I'm storing it for. And then I'm going to use that to answer the last part here. So our formula is A is equal to 900E. Now we have that interest rate stored to more accuracy than just 3.5% in our calculator. So now to get that value, it would be 900E to that stored alpha R value times 10. 900 E, and we're going to put alpha R. That recalls that stored value times 10. So we get about $1,270.79. All right, so one of the expectations when working with these problems is avoid intermediate rounding by using the store button on our calculator. Okay, typically, that's going to mean when you're solving for an interest rate, to make sure that you keep that interest rate as accurate as it can be given the precision of your calculator. Now, we're going to do other formulas for the remainder of this chapter that are very PERT-like related. For any of these formulas, we're going to be avoiding that intermediate rounding. Usually it involves the R or whatever variables in that slot. And this is how you're expected to be able to handle. All right, we're going to jump down to number 2. Okay, determine the principal that must be invested at 4.7% compounded monthly so that $250,000 will be available for retirement in 30 years. Okay, we're compounding monthly. So as soon as you see we're compounding something other than continuously, it's the other interest formula. Okay, determine the principal that must be invested So the P, that's our variable, invested at 4.7%, compounded monthly, that's 12 times per year, and we are looking for retirement in 30 years, and the amount that we want is $250,000. Okay, so basically what we need to do is divide both sides by this whole value right here. But again, we want to keep that as accurate as we can. So let's see what we can do with this one. So 1 plus 0.047 divided by 12, we get that value. And we're going to raise that to the 12 times 30 power. So that number is what we have to divide into 250,000. So 250 to 3,000, and then we divide it by answer, and that will give us our number that they're asking us for. I guess I'll copy it right here. 61204.5. So we'd have to invest roughly $61,204 in order to reach that retirement goal. All right, we are going to skip down to 4, and then just this one right here. Sheet of scrap paper. Okay, complete the table for time t necessary for p dollars to triple if interest is compounded continuously at rate R. All right, so compounding continuously. We are back to PERT. Now it's asking us for the amount of time for our money to triple, but instead of giving us a specific amount, like it did here, oh, I'm sorry, where do we do the double? Like it did here, we're just saying P dollars. So here's how we're going to handle this. P, 3P. And whatever this is, 3P, went the wrong thing. Whatever this is, that's 3 times that. And we have E, the interest rate is 3%, 0.03. And then tripling time is what they're asking us for. Now, an interesting thing about doubling time and tripling time is it's actually independent of the amount of money that you invest, because our first step is to divide by P anyway. Okay, just like back here when we did the first doubling time, 3,000, 6,000, after we divided by 3,000, that was 2 anyway. So whatever this is, if that's double, that's always 2. Whatever this is, if that's triple, that's always 3. And then we just have a couple of simple steps left. Natural log of both sides. Divide by 0.03. And that will give us our tripling time. And you're looking at about 36.6 years. All right, just for the purposes of if you wanted to go ahead and practice a couple more on this page, the answers turn out to be for this one, about 4.1%. That's about 16.9 years. It's about 15,661.37. That's about 10.7 years. Okay, this one here had a whole bunch of different parts to it. I don't have those numbers in front of me. I'll look for those in a second. This turns out to be about 15.7, about 10, and about 7.3. This is about 9.2, And do I have... I do not have the other answers. Apologize for that. No, this is not it. It's a different answer. That was the answer that's up here. Do not have the values to those. Apologize for that.